Hello everyone, welcome to the alcohols reaction chapter. This is going to be a very short lesson here. We're just kind of reviewing ways we know how to prepare alcohols before we get into some of the reactions of alcohol. So how do we actually get an alcohol? Well, if we remember from Organic Chemistry 1, you remember the SN2 and SN1 reactions, right? Depending on how crowded your alkyl halide is or how crowded your leaving group is, that OH can come in as a nucleophile and add itself on. We remember the alkene reactions, that's just double bond carbon-carbon. Remember there's stuff like oxymercuration, demercuration, hydroboration, oxidation. There's just tons of reactions that we're going to look at, so let's get into that. Okay, so for our first set of reactions here, I want to revisit SN2 and E1. It's quite simple. We need an alkyl halide or any compound with a good leaving group. So here, for example, I have, what is this, bromobutane. So we're going to react this with sodium hydroxide. And if we remember, this is an ionic compound, so the sodium gets a positive charge while your hydroxide gets a negative charge. And what will happen is this hydroxide is going to come over here and do what's called backside attack. It's going to kick off the bromine. So a resulting compound looks something like this. And that is SN2. Right? Hopefully you remember that from Organic Chemistry 1. If you didn't, it's perfectly okay. We're just going to lay our foundation works. You've probably only covered synthesis strategies and radicals up to this point. So maybe these old reactions are a little bit old to you and you need a little reminder, and that's perfectly okay. Next, I want to move on to SN1, kind of like SN2, but instead of occurring all in one step, we're going to get a carbocation intermediate. And this will have a unique impact on our compound. So SN1 means, the SN reactions, it means substitution by nucleophilic attack. That's what the SN stands for. 2 just refers to the kinetics of it. SN2 means it's a bimolecular process. It happens with 2 different things occurring at once. So that would be the removal of bromine and the addition of hydroxide. SN1 just looks at, okay, the first slow step is going to be that bromine leaving. So the reaction goes as fast as that bromine can leave. So bromine's going to leave here. We're going to get a carbocation. And maybe you remember this, but remember carbocation stability? The more substituted a carbocation is, through hyperconjugation, it's going to be more stable. And we can achieve a higher carbocation substitution here by doing a hydride shift. And if you remember those, it looks something like this. The hydrogen here is going to see that positive charge and be like, oh no, you are very unstable. It's going to rearrange, and we are going to get this here. We're going to get the, we're going to get the positive charge. I'll draw the positive charge in blue. We're going to get the positive charge on a secondary carbocation instead of a primary one. And now our hydroxide is ready to attack. Kind of taken a while. He's a little slow, so sorry about that. And we'll go like this, and we'll attach as such. Okay, and some notes about these SN reactions, substitution by nucleophilic attack, is that I want to point out for this first reaction we have here, you need a polar aprotic solvent, right? We don't want any competition from that protic solvent to possibly protonate our strong nucleophile or just interfere with the reaction. So we'll use something like acetone for this. Acetone is very nonpolar, and therefore it's not going to interfere with our reactants. Here we have a carbocation, and we need to stabilize it. So we can actually do that through using a protic solvent, right? So what happens here to stabilize this charge is we could use something like, trying to think of just a simple solvent, H2O. The H2O will make this reaction go better because we are allowing that positive charge to be reduced, right? Because if we have a bunch of oxygens, right, so these are our water molecules, they're going to interact with that positive charge because this is partially negative and low and kind of cancel each other out. That's what I'm trying to get at. So remember, those are the SN reactions. And now I want to get to the alkene reactions and see what we can do with those. Okay, so hopefully you remember these reactions here, but if you don't, it's not a problem. We're going to look at each of them individually. We're going to get 3 unique products here. And if you remember, we're going to start with what's called acid catalyzed hydration, where the acid is going to act as a catalyst and water is going to come in and act as our nucleophile. So how can we kind of predict our product here? Well, I want to just draw the mechanism for each. Very basically, we won't get into the hydroboration oxidation. That one is extremely complex. When you get to the oxidation step with H2O2 and sodium hydroxide, that is nothing that I would want an undergrad organic chemist to have to remember. I don't even remember it really, so I'd have to look at a resource. It's stupid. I can't show you the one for what's it called, oxymercuration, demercuration, because that's actually a fair mechanism. That's not terrible and will make you want to cry. Okay, so let's get right into acid catalyzed hydration. We'll start with our alkene, and we're going to come in with acid. We'll just draw that as a proton. It could come directly from H2SO4. It could come from H3O+. Doesn't matter. So just for simplicity, I'm going to just say H+. Now this double bond reaches out and is going to pick up that hydrogen, and it's going to go to the less substituted side. Remember Markovnikov's rule to give us a carbocation on the more substituted carbon, and thus more stable, right? We wouldn't expect it to go to the other side. Now here we could make a tertiary carbocation. Remember we saw that just a second ago. And we're going to have a hydride shift here, so that hydrogen comes around and he's like, hey, join the party on the other side. Be more. Hydrogen's kind of like the dude who's like, you know what, I'm a very selfless guy. You can have my seat in the fun party. So he goes from the secondary carbocation party to the tertiary carbocation party, and therefore he's awesome. He's happier that way. He's more stable, he's chilling. He gets some sunglasses because that's really cool right there. Okay, so what comes next? So we have that carbocation. So what's going to happen here is we're going to have an equivalent of water come in. And this should be assumed it's your solvent. So this is going to happen quite happily because there's millions, gazillions of them around. So it's going to attack that positive charge and attach itself as such, giving us this compound here. And you're like, uh-oh, oxygen has a positive charge. It don't like that. Remember how I said this was acid catalyzed? Well, you could either take the conjugate base of our strong acid, H2SO4, or just an equivalent of water. You will most likely not see your strong acid get protonated as much as the solvent would, because you only have how many moles of this in solution, but you have how many moles of water? You have a lot more water. So you're most likely to see it from water doing this deprotonation instead of our conjugate base from our strong acid. And that's important, but I know most professors don't really care which one you pick. Just try to stay as consistent as you can. So we're going to have a brown arrow this time come over to that hydrogen, and oxygen is going to receive some electrons, and we get our final product of an alcohol, a tertiary alcohol. So we went from this alkene here, and we went all the way to this compound here, this beautiful species, a tertiary alcohol. So we'll write tertiary alcohol. As the cool kids at my college, it's called Jackson Street. Alcohol is their favorite thing. Don't get into alcohol, kids. It's very bad. Okay, so we're now on to the oxymercuration, demercuration. This is a pretty fun mechanism here. Remember that that mercury acetate is going to reach out to form this intermediate. I'll draw our starting material in black, and then whatever happens to that in a different color. So we're going to have our mercury make a three-membered ring here. Mercury, and then here's its little acetate buddy. It loses one of its acetate, but then it gains, or it doesn't gain one, it just keeps one of them, and it becomes positively charged, which is our electrophile. That electrophile is going to get hugged by those pi electrons. It's like, I'm so happy. Now, as our nucleophile, in this case water, this could be an alcohol if we want to make ether, but in this case we want to make an alcohol, so we're going to use some water. So I'll just draw that here. As water approaches, it's going to want to make the carbocation with the least amount of positive charge, or the most stable positive charge. So when it comes to this side here, it's going to have, it's going to increase in, this carbon here is going to increase in its primary positive carbocation character, you could say. But if it approaches this carbon, it's going to start increasing in secondary carbocation character, and that's lower in energy. So it's going to attack from this side. It's going to go whoop, and it's going to be like, you know, Mercury, I know you're not really one for electrons, but you can have some here. And we're going to get this compound. Oops. Oh my goodness, give me a normal, oh, it's because I didn't have it selected. Come on, give me black. Give me the, one's purple, guys, so we're going to have to go with purple. I apologize. And the resulting part of this is that we get our mercury acetate on this side, and we're going to get our water. And notice how we didn't really go through a carbocation intermediate. We saw some carbocation character, which directed where that nucleophile was going to attach, our water. So let's go here. And because there wasn't a true carbocation, there's no way for that hydrogen to shift over. So what we see here is we just get this molecule, and then it's going to get deprotonated by another equivalent of water. There's no really other good species for deprotonation, so we'll just go with this one here. And we just make it an alcohol. And then through the sodium borohydrate, one second, locked into draw, it's going to get rid of that mercury acetate. So we want to get rid of that mercury. So we do that through sodium, the boron here, hydrate. And this is an ionic species, right? So this has a negative charge, this has a positive charge. Now we will actually see sodium borohydrate come back up. It's called a reducing agent, and we'll see more when we get to ketone reduction, turning ketones into alcohols. We're going to see how this reagent is critical to doing that. But just to kind of show you, give you a little sneak peek here, we're going to extend one of the bonds here, and we're just going to have the BH3 here. Only one of the hydrogens matter. All right, and this has a negative charge, and we know that if we could make a negative charge and do a neutral charge, it's going to be a lot happier. So what it does is this hydrogen is going to snoop around, and it's going to whack that mercury acetate right off. And in its place, it's going to leave a hydrogen. And would you look at that? We have our secondary alcohol product. So we saw a tertiary one here, a secondary one here. And as you might be able to guess, or maybe you remember, which would be amazing, is we're going to get a primary alcohol, right? So in here we saw that mercury acetate kind of locked that that reaction center in that one specific area, right, where that alkene was. Here it will kind of do the same thing. So remember that, and I'm not going to draw the mechanism for this one. Again, it's too stupid, but remember the key here to this reaction occurring is what we call steric hindrance. So if I'm that BH3 group, and I'll just be, so we have two H's here. Which way is this molecule going to approach? Is it going to approach from the bulky side? So you can see we have a lot of bulk here. And then we have two hydrogens and a boron on one side. That's pretty bulky. No, there's going to be too much steric hindrance. So if this molecule is going to have any sort of successful reaction, it's going to want to do so in a way where it's not going to be repelled due to its steric hindrance. So I'll just draw that special hydrogen this way. So if we look at our steric interactions now as the molecule approaches that alkene, we notice that we have just a little itty bitty little baby hydrogen right here approaching this big fat bulky side. Now that's not good, but it's better than bulky BH2 approaching a big hydrocarbon. So it's going to attack this way, and because of that, that hydrogen gets attached to the more substituted carbon, which is like a crime, but to Markovnikov, you should say, but it does it anyways because that's chemistry for you. And we're going to have our boron attached to here. Oops, did not draw that right. Let's draw it like this, BHH. And remember, this will repeat 3 times, right? So now this side's the bulky side. This side's the bulky side, and this side's like the happy side, right? So it will attach, and it will do, it will trialkylate itself, and then through a series of oxidation through H2O2 and sodium hydroxide, we're going to notice that we are going to, as our final product, get this. And you were probably never asked to draw the mechanism. If you were, I apologize. That is terrible. That's like a 10, 11 step mechanism right there. But yeah, we get this product here. So this is a primary alcohol. So let's just do a quick little review here. We do acid catalyzed hydration. We get a tertiary alcohol in this example. Could be normal. You could get the same product for any given reaction. Just depends which reagents you use and which starting material alkene you use, right? And we have oxymercuration, demercuration, hydroboration, oxidation, right? And those all lead to different products in this specific example. So hope you guys enjoyed that video. That was review. It's always good to keep that review in mind when we're moving forwards, because in synthesis problems you might be given an alkyl halide and you have to make an alcohol, and it's good to remember those reactions. In our next episode, 12.2, we're going to look at ketone reduction and what that is all about. So I'll see you guys in that video. Goodbye.